So in this lecture, we cover what's known as the E2 reaction. And so of the SN1, SN2, E1, and E2, this is the most complex. So this has a lot of different characteristics of it that you have to know. Okay, so this would be an example of a recipe for an E2 reaction. So if we take this alkyl halide, so it's secondary, right? So that's okay for SN1, okay for SN2, okay for E1, okay for E2, as we'll see. So now the base are nucleophile, so this is strong. So that's going to eliminate SN1, and that's going to eliminate E1. Strong is good for SN2 and E2. And then we throw in heat, and that's going to eliminate SN2. That's great for E2. So this is going to fit the characteristics for an E2 reaction. Okay, so what happens in this reaction is, so this is a nucleophile, but also a base. And if it's going to do SN2, it's going to act as a nucleophile. If it's going to do E2, it's going to act as a base. Okay, so, and SN2 and E2 are generally always in competition with each other. Not always, as we'll see, E2 is okay for tertiary, whereas SN2 is not. But if it's primary or secondary, then SN2 and E2 can be in competition with each other, just like SN1 and E1 is in competition with each other. So if this did an SN2, then your product would be that, right? Where the OH just substitutes for the bromine. So that would be, if it did an SN2, then that would come here and it'd kick that off. So this would be without heat. So if you have heat though, then what's going to happen instead is the hydroxide is going to act as a base. And what do bases do? What's the definition of a base? It's a proton or hydrogen proton acceptor. So what's going to happen is you can take a lone pair of electrons on oxygen, make a bond to hydrogen, and the electrons in the CH bond are going to become a double bond, and the bromine's going to leave. And all of that's going to happen at the same time. So similar to SN2s, we're going to sketch out a transition state showing all of the changes that are happening. Right, nothing's happening to that part of the molecule, but you are breaking this bond to hydrogen, and you're making the bond to the OH, and you're making a double bond to between the two carbons, and you're breaking the bond to bromine. So you're making, breaking, so 4 bonds all at the same time. So that's your transition state, and then that goes on to product. Right, and so just like with an E1 makes an alkene, E2 reactions always make alkenes as well. Okay, so that's the rate determining step, the first step. There is only one step in the reaction, right? So this is, you go through transition state, and then you go on to product. So it's a one-step reaction. So some characteristics of an E2. So similar to an SN2, rate depends on the concentration of the alkyl halide and the concentration of the base. So if you double the concentration of the 2-bromobutane, that doubles the rate. If you triple it, that triples the rate. If you triple the concentration of hydroxide, that triples the rate. Right? If you double both, that would quadruple the rate. And so what does the E2 stand for? It stands for it's a bimolecular reaction. And E again stands for elimination. So what are you eliminating? In this case, in this reaction, ultimately what you ended up doing is eliminating HBr and made a double bond instead. Okay, so similar to an SN2. So for an SN2, you need a good nucleophile. For an E2, you need a good base. And so generally things that are good bases are good nucleophiles, but that's not always the case. There are some things that are good nucleophiles that are not good bases, and vice versa. Okay, heat. So heat favors. Heat favors SN2 over E2. And so for the same purpose, so in this reaction, let's see, you made the side products would be H2O, right? You make H2O there. And then you had the sodium cation and you lost a Br, so you make Br minus. So in this reaction, if we contrast SN2 and E2, so for the SN2, so two molecules become two molecules, right? That's one molecule, and two molecules become two. And for the E2, right, two molecules become three molecules. So that's more disorder. So entropically that is favored. So again, as you heat the reaction up, entropy tends to dominate, and you tend to follow the E2 pathway instead of the SN2 pathway. Okay, so if we look at this one reaction in a little bit more detail, so this is a concerted reaction. So it's one step, right? So there's no carbocation. So there's no rearrangement. So you only have to worry about rearrangement in SN1 and E1, not in SN2 or E2, or free radical reactions for that matter. Okay, so in terms of predicting the product of an SN2, so you're basically going to lose a hydrogen on a carbon adjacent to the carbon with the leaving group. So for this reaction, that would mean this carbon and that carbon. Those are the ones adjacent to the carbon with the leaving group. So you could put the double bond here, or you could put the double bond here, right? If you lost, well, let's sketch these hydrogens out. So if you lost one of these hydrogens, doesn't matter which one, and put the double bond at A, then you could make as a product. Right, so this would be from A. Or if you took a hydrogen from B, so let's call these hydrogens. If you put the double bond at B, so then you could make two products. Because you could make the cis isomer or you could make the trans isomer. So similar to E1 in that regard. So there's three possible alkenes from this reaction. So which one's going to be the major product? Well, this is mono-substituted, this is di-substituted, and this is di-substituted. That's cis. That's trans, so that's the more stable. So that would be your major product in this case. But you do not always get the most substituted alkene as the major product in the E2 reaction. That depends on what base you use. So if we did the same reaction, and we used as the base this instead, so that's what's called potassium tert-butoxide. This is what's known as a bulky base. Then this is going to give the Hoffman product as the major product. Okay, so this would have been the Hoffman product, right? Because it's the least substituted, and these are Zaitsev product. Because they're more substituted. But the bulky base is going to give you the least substituted alkene. And the reason why it's for steric reasons, right? The base is big. So it's going to take the most accessible hydrogen, which is going to be one of them on this carbon. So the mechanism is basically we're just going to take a lone pair, take off any of these three hydrogens, those electrons become a carbon-carbon double bond, and bromine leaves, and it all happens in one step. So a transition state would look like so we're breaking that bond, and it's making a bond to the tert-butoxide, making a double bond and breaking the carbon-bromine bond. And then your major product would be that, which of course does not have a cis or trans isomer. Okay, so this is one thing that you have to keep in mind for an E2 reaction. A small base gives the Zaitsev product. And a bulky base will give the Hoffman product. Right, that's the major product. And so we'll only look at two bulky bases. So one of them will be the potassium tert-butoxide, and another bulky base that we will look at will be what's called LDA. So LDA is this. It's an acronym for lithium diisopropyl. Lithium diisopropylamide, LDA. So it's a bulky base again, so because of the two isopropyl groups. So it's pretty big, so it's going to make it sterically crowded around nitrogen. So it's going to take the most accessible hydrogen, right? It's going to take the hydrogen that's easiest to get to, which again will be the one that's going to lead to the least substituted alkene. So it's going to take one of these hydrogens. And the electrons in the CH bond become a double bond, and the bromine leaves. and you make the least substituted alkene as the major product. So that's the only two bulky bases we'll look at. So the other bases that you see in E2, you can just assume they're small bases, and they're going to lead to the more substituted alkene as the major product. Okay, so if we took another example to illustrate that. So if we contrasted those two reactions, so let's convince ourselves that, well, first of all, what kind of mechanism should this follow? So now we know 5 mechanisms: free radical, SN1, SN2, E1, and E2. So which one is this going to be? So this is a tertiary alkyl halide, so that eliminates SN2. SN1, E1, E2 is okay. There we go. So that's another characteristic of an E2 reaction, is that tertiary is better than secondary, better than primary, better than methyl. So that's the same as SN1 and E1. So the only one that likes methyl first is SN2. Okay, so, why does E2 like, so E2, the reaction is not at that position, right? It's one position away. So the steric crowdiness around that carbon doesn't really matter like it does for an SN2. And if it's tertiary, it's going to lead to a more substituted alkene, so that's going to be favorable for an elimination reaction. Okay, so this is strong. So that's going to eliminate SN1, and that's going to eliminate E1, but E2 is still okay, and this is strong. So SN2 is already gone. So that's going to eliminate SN1 and E1, and E2 is okay because E2 likes strong base, strong nucleophile. So you don't even necessarily need the heat in this reaction because the SN2 is already eliminated for competition. And SN1 and E1 is eliminated because the base is strong. So the only thing that this can do is E2 elimination. Okay, so you've established that it's an E2 elimination. So now you just need to know there's no rearrangement possible in E2. So where can you put double bonds at? You could put a double bond here, A, B, or C, right? And so you just have to keep in mind, so it has to lose a hydrogen from one carbon away from the carbon with the leaving group. So that means that carbon, or that carbon has to lose a hydrogen. And then you make a double bond, and the chlorine leaves. Okay, so if you make the double bond at A, that would lead to a disubstituted alkene. If you put the double bond at C, that's going to lead to trisubstituted alkene. And if you put the double bond at B, that's going to lead to a trisubstituted alkene. So this is a small base, right? How do you know it's not a bulky base or a big base? Because it's not potassium tert-butoxide and it's not LDA. That's the only 2 bulky bases that you have to know. All of the other ones you can assume are small. So that's going to lead to the Sayat-Seth product. So that means put the double bond at B or C because that's tri, and it doesn't matter B or C because they're equivalent. So your major product would be, in this case, that, which is the same thing as, right? Right, those are the same molecule. So that's what you get if you use that base. If you use potassium tert-butoxide, this is bulky. So that's going to lead to the Hoffman product, which is the least substituted alkene. So that means the double bond needs to be at A. Right, so you lose a hydrogen from there and make a double bond, and chlorine leaves, and that's your product. Right, in terms of the mechanism, if you have a hard time seeing that, right? Take a lone pair, make a bond to hydrogen, CH electrons become a double bond, chlorine leaves, and that gives you that. Or if it's a small base, so sketch out one of these hydrogens in the OCH3 minus. Take one of those hydrogens, those electrons become a double bond, and chlorine leaves, and you would get that. Okay, and then there's one more concept here in the E2 elimination. And that's this concept that you have to have it, has to go through an anti-elimination mechanism. So just like with the SN2, stereochemistry was very important. Let's make this different. Okay, we did that reaction. So let's classify the alkyl halide. So this is secondary and benzylic, right? That's okay for SN2, SN1, E1, E2. This is strong. That eliminates SN1 and eliminates E1, SN2, and E2 still okay. This is heat. That eliminates SN2, so the only thing left is E2. This is an E2 reaction. So it's an E2 reaction, so how many places can you put a double bond? Well, you have to lose a hydrogen from a carbon next to the carbon with a leaving group. So that means that carbon, or that carbon, which would mean that hydrogen, right? And this carbon has no hydrogen on it, so you can't put a double bond here, right? Your only choice is to put a double bond at B. Okay, so in E2 reaction, right, the hydrogen that is abstracted has to be anti to the leaving group. If you remember what anti means from the Newman projections, right, this is anti. So if we drew a Newman projection of this molecule looking from this perspective, then what you would see is the front carbon is a Y. Methyl group is on your left, benzene ring is on your right, hydrogen's at your feet, and then the back carbon, bromine's at your head, benzene is on your right, and hydrogen is on your left. And when you do the elimination, that's the hydrogen that has to come off, so it is anti to your bromine. So what's going to happen then is hydroxide is going to take that hydrogen, those electrons become a double bond, and bromine leaves all at the same time. And so if you notice, your two benzene rings are on the same side, and so since all of this is happening at the same time, they have to end up on the same side. And the methyl group and the hydrogen is back from my perspective, and so they have to end up back, both back. So the point being, when the product that you make would have to be that, right? That's the only place to put the double bond. And because it has to be an anti-illumination, those two benzenes are in the same, are both on the solid wedge, so they're both coming towards me, so they both have to end up respect to each other on the double bond, cis to each other. right? So this is the cis alkene. Trans would be more stable. Right, but you can't make the trans. All right, due to the anti-elimination. So the only way to get the two benzenes anti to each other, so we can use a symbol pH for benzene. Phenyl is what that stands for. So if we wanted the benzenes to be trans to each other, we would need to rotate around this bond 180 degrees. So that would put the phenyl, one of the phenols back. So if you rotate 180 degrees, the hydrogen comes up, the methyl group that is back comes out towards me, and the benzene that is towards me, 180 degrees, goes away from me. So if you did elimination there, HBr, then you would get that, the trans isomer, but this is not possible because this is what's known as a syn elimination. Right, with the H and bromine dihedral is 0 degrees, and that's not the way E2 reactions work. The E2 reactions work by the hydrogen and the leaving group 180 degrees apart. So the stereochemistry, so the point being, right, the stereochemistry of the starting material determines the stereochemistry of the product. And that's just like in an SN2, right, where you get inversion of stereochemistry. Right, the stereochemistry of the product depends on the stereochemistry of the reactant. If the chlorine was back to begin with, then the OH would end up front in the end. So E2 is very similar. Stereochemistry that you start with is going to determine whether you get the cis or the trans alkene out. Okay, so let's take one more example to illustrate this. Okay, so Cl is there, H is there. I don't know. Okay, so if we did this reaction. Okay, so how many places are there to put a double bond? So this is an E2 first of all, right? That's secondary, this is strong with heat, and that's the recipe for an E2 reaction. So anytime you do an E2 reaction, anytime you do an E2 reaction at a chiral center, you need to pay attention to stereochemistry, meaning anti-elimination. So we didn't worry about that when we did these examples because you don't have stereochemistry shown to you, so you don't have to worry about it because you don't know where everything is at in 3 dimensions. But if I give you the molecule like that, you know where everything is at in 3 dimensions because of the dash wedge structure. So that means I'm basically probably trying to test you over whether you understand this concept of anti-elimination or not. So same is true here. If you're given a chair cyclohexane, you are shown where everything is at in 3 dimensions, which means I'm probably trying to test whether you understand this concept of anti-elimination or not. Okay, so how many places are there to put the double bond? So you could put the double bond here or there, right? So you could either make that, which would mean you lost a hydrogen from that carbon, or you could make that, which means you lost a hydrogen from that carbon. Right, so that which means you lost that hydrogen. Okay, so this is an E2 reaction. You have to worry about anti-illumination. That hydrogen is not anti to the chlorine, it's gauche to it. So you can't take it. So you're forced to then take a hydrogen from carbon B. So if you sketched out where these hydrogens are, so one is there equatorial and one is there axial. So that's the one that you can take. So in cyclohexanes, they both have to, so the chlorine and the hydrogen has to be diaxial to each other. So that way they're anti. So that means you can only take this hydrogen, and then the double bond would go here and chlorine would leave, and that's the only product that you can make. So even though that this is di-substituted and this is tri-substituted, tri-substituted is more stable, but you can't make it because of the anti-elimination of an E2 reaction. You can only make the di-substituted alkene, so that's your major product. If, however, you started with this stereochemistry, well now, so let's see, KOH, heat. So again, there's two possible products. You could put the double bond there. Or you could put the double bond there. And in this case, that's your major product. Because now the hydrogen is anti, right? That hydrogen is anti. Since they're 1,2 with respect to each other and both axial, they're anti to each other. So now the base hydroxide can take this hydrogen. Those electrons can go there to make a double bond, and the chlorine can leave. And now your major product is the tri-substituted product. So again, the stereochemistry of the starting material determined which product you could make. Okay, so that's pretty complex reaction that E2 is. There's lots of different nuances that you have to know, whether it's a small base or a bulky base. You get the Zaitsev product or the Hoffman product. If you got stereochemistry involved, is the hydrogen anti to the leaving group or not? If it's not, you can't take it, and you have to take the hydrogen from a different carbon, wherever the hydrogen is anti to the leaving group. Okay, so hopefully that made sense. In the next lecture, we'll take a few more examples of the different reactions and make sure you can put them all together.